It turns out that the intermolecular forces have significant effects on the physical properties of various substances. And so some of these properties include surface tension, the viscosity of a liquid, or the ability of a liquid to flow, the vapor pressure, the ability of a liquid to evaporate, or then also the boiling points, which the normal boiling points are the temperatures at which the liquid will begin to form bubbles in the form cavities within the liquid and at 1 atmosphere pressure, and then finally also the melting and freezing points, as well as the associated temperatures for those processes. We can first start with a discussion of surface tension. Surface tension is a phenomena associated with the intermolecular forces between molecules that occur at the surface of a liquid. Turns out that the forces of attraction between a particular molecule and other molecules within the liquid are such that the net force is acting on that molecule is zero. But if we go and look at the same types of interactions, but for a molecule at the surface of the liquid, assuming that the material above the liquid has very different intermolecular forces than the liquid itself, you see that the net force is no longer zero because of the lack of intermolecular forces that are acting in the vertical direction. So, turns out that the greater the intermolecular forces, the more likely it is that the surface tension will increase. Surface tension can be a significant factor in how various types of objects can interact with one another. So as you see here, the liquid, which in this case happens to be water, behaves as if there's a membrane stretched across the surface of the liquid water. And in fact, if you very carefully place a metal pin where the forces of attraction between the water molecules and the pin are very different, you can actually get a metal pin to float on top of the surface of the liquid as long as you don't break the surface of the liquid. And this then creates the illusion of floating, but these forces are strong enough to overcome the force of gravity on the pin. So these attractive forces can be quite strong, or relatively strong, due to the hydrogen bonding effects in the water molecules. So it turns out that if we break those surface interactions by adding some sort of surfactant or a soap, something like a soap or a possible detergent, then we can really reduce the surface tension effect. So we can compare the magnitude of the surface tension to the types of intermolecular forces found in molecules. And so the table that you see here compares the formulas of various compounds to their surface tension in joules per meter squared. And so it turns out that something like carbon dioxide, which is a nonpolar molecule, and it has a very weak London dispersion forces as its major type of intermolecular force, has the lowest of the surface tensions. If we turn to something like hydrocarbons such as pentane, a little bit bigger molecule than CO2, but still only has London dispersion forces, the surface tension goes up a little bit. If we compare this then to chloroform, which is now a weakly polar molecule, the surface tension goes up further. Bromoform, in this case, not replacing the chlorines in chloroform with bromine, provides greater London dispersion forces, and again, the surface tension goes up a little bit. And then we can turn our attention to molecules that have hydrogen bonding, something like glycerol and water, which have significant surface tensions because of the hydrogen bonding. Another consequence of intermolecular forces is a phenomenon known as capillary action. If you have a liquid that is placed within a glass tube of some sort where there are significant attractive forces between the water molecules and the surface of the glass, the liquid will creep up the sides of the glass and adhere to the glass in some fashion. And so in this case, this creates the so-called meniscus, and this is, as you see here, causes the curved shape at the interface between the liquid and the air within the capillary tube. This is a very important force when it comes to plants and their ability to suck water up the stem, and then also very important in terms of how soil interacts with water. So, and this then has all kinds of important ramifications for agriculture. It turns out that this is very different for something like a liquid, like mercury interacting with the glass, where the attractive forces of the interactions between the various metal atoms is actually greater than the interactions between the mercury atoms and the glass itself. And so in this case, the meniscus that is observed, the curved shape, is actually a convex shape, and as you see here in the diagram. Another property associated with the intermolecular forces of a liquid is the so-called viscosity, which is a measure of the ability of a liquid to flow. And so if we were to compare various liquids to one another, essentially this is the ability to flow is due to the ability of the various molecules to slide past one another. And of course, this is dependent upon the degree of intermolecular forces. The stronger the intermolecular force, the higher the viscosity. So as an example, we can compare glycerol to that of water. While both of these have hydrogen bonding, the glycerol has more than one OH group within the molecule and can have multiple hydrogen bonding interactions with other molecules, whereas the water molecule, while it does have that optimal ratio of hydrogens to lone pairs, the number of hydrogen bond interactions per molecule is slightly less than that in glycerol. As a result, glycerol is relatively viscous and is often used in food products such as ketchup to thicken the ketchup. Much like the surface tension, we can look at the so-called viscosity of the various liquids that we compared before, and indeed the viscosity values parallel very nicely the types of intermolecular forces. Again, carbon dioxide, having nothing but London dispersion forces, has pretty low viscosity as a liquid. And pentane also flows relatively easily, chloroform, and then finally we get to water, which has significant hydrogen bonding, so the viscosity is quite a bit greater, and then finally glycerol, which has the highest viscosity. Boiling is a phenomenon that is significantly affected by intermolecular forces because we have to be able to break all of the intermolecular forces of the liquid to get a molecule to go into the gas phase, where there is essentially no intermolecular interactions because of the great distance between molecules. A good example of various substances that have nothing but London dispersion forces, and the effect of the increased polarizability of the electron clouds is shown here, where we look at the boiling points of the noble gases. Helium, being the smallest and least polarizable, has the lowest boiling point at about 4 Kelvin. And as we go to larger and larger noble gases, the boiling point steadily goes up, all the way to the point that the xenon and neon are gases, but they have boiling points that are not that far below room temperature. If we look at the boiling points of some of the main group elements in which they have been bonded to hydrogen, we see that for the compounds in group 5, 6, and 7, we see a trend much like we observed for the noble gases, where the heavier the central atom, the higher the boiling point, and this trend mirrors the increasing London dispersion forces and polarizability of these molecules. One question that is quite interesting is, if we were to extrapolate the trends back, what would be the boiling points of water, HF, and ammonia? And you see here the potential boiling points of these substances shown with question marks next to them. However, this is what the boiling points would be if all there were London dispersion forces acting on the molecules. But in fact, if we look at the boiling points of water, HF, and ammonia, their boiling points are significantly higher and not what we would predict based upon simply London dispersion forces. And this is a consequence of the hydrogen bonding effects that are observed for these molecules. Finally, we can compare the boiling points for the second period elements in which the atoms are bonded to hydrogen and observe the effect of the hydrogen bonding. And so this table presents the data, and you see that if we start with methane, we have a significantly low boiling point, consistent with there being nothing but London dispersion forces. If we go to ammonia, now we have the possibility of not only there being dipole-dipole interactions, but also the hydrogen bonding effect. So the boiling point goes up significantly. If we go and then look at water, the boiling point goes up even further, but then as soon as we get to HF, the boiling point goes down again. And then finally, neon, the boiling point is nearly the same as methane. This can be compared to the ratio of lone pairs to hydrogens, and you see that the ratio for water is such that there is a 2-to-2 ratio of the hydrogen atoms within the molecule to the lone pairs. This optimizes the hydrogen bonding interactions so that the structure is producing the greatest overall intermolecular forces. And as you can see here, the optimal structure is such that each of the hydrogens gets to interact with a lone pair on a neighboring molecule, and each of the lone pairs gets to interact with a hydrogen, and this locks the water molecules into a particular shape. However, in the liquid phase, of course, these are broken to some extent due to the thermal energy, and these water molecules can move past one another and can flow.